Okay. So what is XV6? It's a simple Unix-like pedagogical operating system. It is used for teaching purpose. It is nothing but re-implementation of Dennis Ritchie's and Ken Thompson's Unix version 6, which is popularly known as V6. And as because this V6 we are trying to develop on x86 architecture, that's why it is known as XV6. So XV6 loosely follows the structure and coding style of V6. This whole operating system is implemented in ANSI C for x86 based multiprocessors, and that's why the name XV6 is there. XV6, as I already told you in lab class, XV6 provides a chance to understand operating system at a very low level of abstraction, and that too at the source code level. But before embarking upon the details of XV6, a bit of familiarity with x86 architecture and instruction set of x86 is needed. I believe you people have done some kind of assembly language and instruction set architecture in your computer organization course. You are going to do 8085 assembly language and 8086 assembly language in your microprocessor course this semester. But I'll be telling you some of the basic instructions and how the instructions are handled and how the format of instruction is, which are going to be utilized in code of x86 in this lecture, just to make you a bit familiar about x86 architecture. Now, if we talk about registers in x86, there are some general purpose registers. If you have started working in microprocessor 8085, in microprocessor 8085, BCD, HL, all those registers are there. In x86, these are EAX, EBX, ECX, EDX, ESI, and EDI. These are general purpose registers which are used to store variables during computation. And then there are two important registers, EBP and ESP, which are used to store the address of base and top of the stack. Stack is an important concept or important artifact in assembly language programming. During function calls and all, you need to use a stack. And where the stack is located in process address space, to identify that, to locate the stack, these two pointers are there. The base pointer means base address of the stack, and top of the stack, what is the current top of the stack, that is that pointer is stored in ESP register. So there are general purpose registers, there's two stack register, and then program counter register, which is known as instruction pointer in x86, EIP. In addition to program counter, stack pointer, and general purpose register, we have segment registers. So in a program, there are various segments. Fine. In Intel 86 terminology, known as code segment, data segment, extra segment, stack segment, and so on. And these registers store pointers to these various segments. How to quickly locate where is the stack segment, where is the code segment, where is the data segment, extra segment. You're not required to know much detail about this. I'm just mentioning them because in code, at some places, you may find use of these registers. So you are not required to go into detail. If somebody is teaching you 8086, you will be knowing about these registers. Then there are control registers, CR0, etc. We'll be looking at some control registers in our memory management module. Uh, like for example, CR3 register holds the address of page table of the current process. And that page table, I told you, is an address translation map to convert virtual address to the physical address. Now, some common instruction which you may encounter in code of x86, and these common instructions are move instruction, most common, move source to destination. So you can provide two registers here, and move instruction actually moves contents from source to destination. The pop and push instruction. Pop instruction pops the value at the top of the stack, which is pointed by stack pointer, ESP. And push instruction pushes the argument provided on the top of the stack. Pop to take value out of the stack, push to push value into the stack. There are variation of push and pop known as push A and pop A. To push pop all general purpose registers, suppose you want to push all general purpose register in one go, you'll be using push A. Or you want to pop all general purpose register in one go, then you'll be using pop A. Jump instruction, when you want to change the sequence, control sequence, when you want to convert if then else or loop kind of instruction into assembly language, you need to jump above or below in the program. Fine. So this jump instruction changes program counter to the instruction address provided. So program counter executes, is normally program executes one by one and program counter is incremented to the next instruction. But when jump instruction is there, you may leave many instruction and jump to another location in the program. So within a program, if you want to change the control sequence, then jump instruction is used. Call is for function call. It's a call instruction when you want to jump to the subroutine, and then after executing the subroutine, you need to return to back to the main function or the function which has called. Jumps to the address of the function provided after storing the return address on the stack. So when you jump to any other instruction, any other function, you store the return address on the stack. And if there is a call instruction, there would be a return instruction. Returns from a function to return address stored at the top of the stack. So to call a function, a call instruction is there. To return from that function back to the original function, the return instruction is there. Some of the above instruction can have letter appended at the end. You may Google it and know more about this, just to indicate the different sizes of register. Fine. In x86 architecture, the sizes of register are variable, 22-bit, 64-bit, 16-bit, and these letters indicate the sizes of register where you want to move some content or you want to push any content on the stack. A little bit of revision is required. Revision in terms of function calls. And I'll spend some time on this because this is important. The operation of a stack. As we have seen before that a process address space, in process address space, there are two areas. One is kernel reserved area, you know about that. And then there is a stack and heap. So heap grows from bottom to top and stack grows from top to bottom. Process allocate an empty area for the stack Whenever a process is created, an empty area in a user space is created for the stack, and that process make these stack pointer and base pointer register to point to the bottom of this memory region, and that is always going to be the highest memory address. The stack grows upwards. It starts at a high memory address and moves towards the lower memory address. So don't get confused about this. The simple thing here is that whenever you want to push anything into the stack, actually the memory address will be decremented. Means because the stack is growing from higher memory addresses to lower memory address, whenever something is pushed onto the stack, the memory address is going to be decremented. Pushing something onto stack decreases the value of the memory address stored in ESP. EBP will always stay at the bottom of the stack unless explicitly changed. So this is how stack operates, and let me explain some more things which are important. Whenever you make a call, there are going to be two functions. One, a caller function, the function which is calling, and other is a callee function, the function which is being called. So there are some registers which are always going to be saved by caller, and these are EAX, ECX, and EDX. So before calling any function, suppose you want to call any function, you need to save these registers. These are caller save register because you are not sure whether the values stored in these registers are going to be changed or not. So you will save these registers EAX, ECX, and EDX. Registers that are saved by caller are the entity that makes the function call. Similarly, there are callee save registers such as EBX, EDI, ESI, and EBP that must be saved by the callee, and they are restored to their previous values when returning to the caller. So before a callee function can execute, in the code of callee function, these registers will be saved. Before a caller function can call, these registers will be saved by the caller function, the code of caller function. Callee places the return value of function in the EAX register by convention before returning to the caller. That is important. So there are two things. One is return address that is saved on the top of the stack. And the another thing is if callee function is returning some value also. So those values or the value will be always stored in EAX register before returning to the caller. This is important. Please make a note of this. That callee places the return value of the function in the EAX register by convention before returning to the caller. And caller can read the function return value from this register. Let's move to whiteboard to understand a bit further. So let me revise the things. Some general purpose register, program counter known as EIP, segment register, some control registers, some normal instruction, jump, call, return, pop, push to stack, move instruction, stack operation from higher memory to lower memory. Whenever a item is pushed onto the stack, the memory address value is decremented. Whatever is stored in the stack pointer is going to be decremented. There are caller save registers and callee save registers. And return value is always going to be saved in EAX register by convention. And now you can understand why caller is saving EAX. Caller might be doing something with EAX. Suppose the main program might be doing something with EAX. Before calling the function, the EAX would be saved, because later on this EAX will be used by callee to store the return value, and that is the concept of saving the register before actually making the function call. And there are designated registers which are going to be saved by caller and which are going to be saved by callee. Let's move to the whiteboard to understand a bit further. Now suppose I have a main program. I'm writing in high level just to make the things more comprehensible. And suppose this main program is calling a function with argument A1, A2, A3, and A4. There is a function, suppose I say this as function fn1. So some function fn1, these are the arguments which are passed. This is calling function fn2, say b1, b2, b3 are the arguments. Now how the things are going to happen? So let's see let's see what is happening in a stack. So this is higher memory, and this is lower. Means the addresses here are higher than addresses. So currently both EBP and ESP are pointing to the bottom of the stack when main is executing. When this function is called, so you will create space in stack. So when we convert this high level into assembly language, you'll find that ESP is getting decremented. Value of ESP is getting decremented. How? Depending upon how many items you want to store. So callee save registers are going to be stored here. Then from right to left, these arguments are going to be stored. A4, A3, A2, A1. And as you keep on storing the values, your ESP is shifting to the from higher memory to the lower memory. ESP is shifting. And finally, this is important, at the top you would be storing return address. What is return address? The next instruction after this function call. Now in totality, all this from current ESP to EBP is known as stack frame. One stack frame. Okay, you switch to this function, you started executing. Now there is another function call. So in this case, what will happen? This base pointer will also be shifted. Now this callee will become a caller, and fn2 will become a callee function. Here it was caller main and it was callee. Later on fn1 becomes caller and fn2 becomes callee, and there can be nested and recursion, whatever you have done. So what will happen? This EBP will be shifted, and now again, depending upon how many values you want to store on the stack, that much is created in the stack by decrementing the value of ESP, which is currently here at the top of the stack, is decremented 1, 2, 3, 4, 5, depending on how many value you want to store. Here, after storing some callee registers, you will be storing from right hand to left hand B3, B2, B1, and finally the return address. Return address. Got the point? Any confusion to anybody? Any confusions to anybody? Yes, Aman.
No, sir.
Why we are saving these arguments? Yes, Aman.
Sir, because means we have to pass it to them in function.
So why we are saving it?
Because sir, we will be using it inside that function. Means when we call any function, then we will be using those argument inside our function. So same thing.
How you pass arguments? If we talk in terms of assembly language? Anybody? Yeah, Abhigyan? the arguments which you are passing, how actually they are passed at lower level.
Sir, we place them in stack.
You just save them in the stack.
Yes, sir, in the next stack frame will form, and using the EPP, we can take back the arguments.
Okay. You are pushing the arguments to the stack.
Yes, sir.
But the problem here is, suppose while executing fn1, I need argument a1. How to get the value of a1?
Sir, we have base pointer updated like about the return address. From there, we
Just
can go
just
2 steps
just
down.
stick to this. And that's why I have given you that you need to, there is a convention that you need to store the things in a stack from right hand to left hand. And how to move through it, depending upon the top of the stack and number of argument, you can somehow go and refer the things. In addition to that, we have another pointers also known as frame pointers, frame pointer register, global pointers, and so on. So within a stack, if you want to refer some item, not every time you are required to use EBP or ESP. That's what I wanted to tell you. Okay. So within a stack frame, if you want to refer, there are another pointers also in x86, which I am not describing it clearly, but there is a way to refer to items within a stack with these pointers. Now what is going to happen, suppose fn2 completes and now fn2 returns. Where it will return? Top of the stack. Top of the stack will be having return address. So fn2 will return here. fn1 is completed. And as and when you return, what will happen? The pop operation will be done. Just to delete all these items from top of the stack. Because your work is done. fn2 work is done. Argument work is done. Save register work is done. You have restored the registered, everything is done. And now you just pop the items. So one stack frame is created and deleted as and when you return back. Where to? As soon as you return back to the top of the stack location, everything else will be deleted. Now again, top of the stack is having what? Return address. You return back from here to here using this address. And now you can carry on with function 1. If there is any return value to be passed, that will be stored in EAX register. So EAX is saved here. It may so happen that main is doing something with EAX, some temporary value or some variable is stored in EAX. So EAX is saved here. In anticipation that EAX might be overwritten if there is any some return value. Then when you do fn1 and before calling fn2, you again save EAX. in anticipation that fn2 might overwrite it. And suppose fn2 is sending some return value, that would be the current value of EAX register, because previous values are always stored and restored. Are you getting the point? In this way, the function call works. Any doubts to anybody? Brijendra?
No, sir, it is okay.
Aman?
No, sir, it is okay.
Okay. Aman?
No, sir.
Clear?
So can you explain the last part again, sir, that EX?
Okay. The last part is, suppose during the execution of main function, EAX is a general purpose register, can be used by main function. Suppose it is getting used by main function. So before calling another function, EAX will be saved on stack. EAX value will be saved on stack, and EAX is means whatever is there in the EAX is saved on stack here. Call is save register. Now suppose fn2, fn1 return some value. fn1 will write the return value in EAX register. Suppose आप कहते हो ना int t equal to some function call. Suppose the function is returning some value, some integer. So that return value will be stored in EAX register. Now you don't have any problem because you have already saved the EAX register, which was having the value of main function when main was executing. It is already there in the stack. So when you return, main will read the EAX register and consider it as a return value, and then later on will pop the EAX value which was saved in stack and populate the EAX register. Got the point up again?
Yes, sir.
Because registers are less in number. Fine. You need to take the help of a stack. There are less number of general purpose register which are required for the computation, ALU computation and all. So whenever you want to do any computation or calculation, things has to be brought back from main memory to CPU register. And these add, delete, add, subtract, multiply operation can only be applied on register. They have to be brought back into some register, and then they can be applied. So if you are already using EAX register in main function, before calling the another function, you have to save the value of EAX register in memory. In memory where? On stack. And that's why in slide it is written as caller save register. Caller will save EAX register because we know later on EAX register is going to be used by callee function to store the value of store the return value. Got the point? Everybody is clear about this? Yeah, Anchal Tiwari?
Yes, sir.
If there any doubt, you can ask. Anshuman Bhargava?
No, sir, no doubt.
Okay. So let's move ahead. Now let's start the code part of XV6. So let me open the code of XV6. Just give me 1 minute. Let me open the code of XV6 and then it will be clear to you. Just a minute. Fine. Okay. So this is XV6 revision 8, which we are using. This is the source code of XV6 revision 8. Is it visible, Vijendra? The
Yes, sir,
file,
it is
the file
visible.
is okay. Then no problem. Now let's see how we can handle interrupts. First of all, our focus is to handle interrupt, and that interrupt will lead to handling system calls, and that will lead to later on creation of process, because fork is also a system call. So in XV6 or Unix or Linux, there is a data structure known as proc data structure, which actually corresponds to your process control block. So the process control block, remember the slide of process control block we have seen in the previous lecture. So whatever was there in process control block is here in operating system code in form of a structure known as proc data structure. You can see the struct proc. It starts at line number 2353 in code of x86. Whenever I'll teach the code, I'll always mention the line number so that later on you can locate it easily by after seeing my slides. So here you can see a lot of information is there in struct proc. What is the size of process memory? What is the page? Where is the page table of this process? What is the state of the process? What is the identification process ID? Pointer to the parent process, uh, open files, current directory where this process created, what is the name of the process, and so on. But we are not focused to all these other elements for a moment. Our focus is these three elements of this structure. The pointer to the kernel stack. Remember in our lecture, I told you that in every process image, there is a OS area or reserved area. And in that reserved area, there is a kernel stack. When you make a function call and a kernel code is executing and it is making a function call, then you need to have a kernel stack. At that time, you cannot utilize the user stack because user stack is for user mode. Kernel stack when you require to execute the kernel code or operating system code. So this is important here. Bottom of the kernel stack of this process. This is one information. Pointer to the bottom of the kernel stack of this process. Then pointer to a the trap frame. Trap frame is another structure. This is structure pointer. Fine. So trap frame of the process. And then another structure context is there, which saves the context of the process, which is having the context of this process. Context means all the detail of that process. So we are focusing on three elements: pointer to the kernel stack, pointer to the trap frame, and pointer to the context structure. Fine. So where this proc structure is there in the XV6 code, so it is on line number 2353. Let's see. Control F. 2353. And we'll be able to see that. Here it is. So let me maximize it. Fine. Now you can see struct proc. Can you see that? Let me open it again. Control F. 3, 4, So at line number 2353, this struct proc is there. Fine. So everything what was there in the slide is there. Fine. Okay. Now let's move further. Kernel stack pointer used when running in kernel mode. Trap frame is needed when process moves from user mode to kernel mode. Whenever there is an interrupt, it may be a software interrupt like system call, it may be a external interrupt like keyboard interrupt, it may be a interrupt due to exception from within program. Whenever there is an interrupt, operating system is going to handle that. And for that purpose, the process will be moving from user mode to kernel mode because process was executing its code, user code, and if there is a trap or interrupt, you will be moving from user mode to kernel mode. And at that point of time, the field of trap frame structure is going to be pushed on the stack to save whatever user context was there. So user might be playing with all those registers, but suddenly what happened, an interrupt comes, and to handle the interrupt, you need to switch to the operating system code. You need to switch the mode from user to kernel. And before doing that, on a safer side, you push everything on the kernel stack, onto the kernel stack, and that everything is the context of the user, whatever user was doing on the CPU at that point of time. And this is, everything is there in the tab frame data structure. There's a very fine line, please be attentive. So I told you another structure also, that is a context structure. Context structure is used when you need to switch from one process to another process. Please pay attention. Trap frame is going to be used when there is no process switch. It is just a mode switch. It's no process switch. You are just writing hello world code, and when you executed printf, you wanted to have a system call, you need to switch the mode. It's still the same process with same PID is executing. Only the mode switch is happening, and as because you are changing the mode, you are moving from user code to kernel code, you save the way we have seen in the function call, you save everything what user was doing in a form of trap frame to the kernel stack. That is not a process switch, only the mode switch is there. What is when the context structure is going to be used? When kernel switches from one process in kernel mode to another process, then the context structure is going to be used. That is another story. Many a time you'll feel, and authors of books are also confused in writing this. Many a time what will happen, suppose there is a keyboard interrupt. So when a process changes the mode to handle the keyboard interrupt, you know that keyboard is a slowest device. It will take some time to handle that interrupt. And due to that keyboard interrupt, you decide to switch the process also. That's another story. That where a mode switch forces a process switch. That's another story altogether. If it's not like that, mode switch does not mean process switch. Process switch is when one process is executing and entirely another process starts executing. That is process switch. What is mode switch? A process is executing in its user mode and then it goes to execute in its kernel mode because that process wanted to have operating system routines to be executed. And as I told you that day, that kernel executes on behalf of the process. So please pay attention on these two structure. Trap frame is needed when there is a mode switch. Context is needed when there is a process switch. It is another story that many a time mode switch can lead to process switch due to multitasking and due to utilization of CPU, due to the scheduling policy of operating system. If some process is waiting for interrupt to be handled, it's better to switch to another process. That's another story altogether. This point is clear to everybody? Yes, Anshuman Bhargava, Anjali Bhatia. It's clear?
Yes, sir.
Amit Rathod, are you there?
Yes, sir.
Any doubts?
No, sir.
You understood the difference between mode switch and a process switch?
Yes, sir.
Okay. Fine. So these two, as I was telling you, these two trap frame and context structures are different and need to store different set of registers in these two situations. These two structures are going to be there on kernel stack, and struct pointer proc has explicit pointers for them just to locate them. You are having pointer for kernel stack already, and using that pointer you can move into the kernel stack, and ultimately you can locate trap frame and context frame. But just to move more efficiently within a kernel stack, these two extra pointers are given so that you can locate the trap frame or context structure, pointer to the context structure or pointer to the trap frame very easily in the stack, kernel stack. That's what is written here in this slide. The struct proc has explicit pointers for them in addition to pointer for whole kernel stack to easily and swiftly locate this structure whenever there is a need. Another important thing. So we have covered one important structure, that is proc structure. And now we are going to see another important structure, that is P table. And what is P table? It's nothing. It is just an array of your proc structure. See here, this line. Struct proc, proc, and proc. Depending upon the number of processes which are running does not mean executing on CPU, as I told you, which are active, which have started execution and maybe waiting also. So struct proc, this is array of the proc structures. So P table is nothing but array of proc structure in the process table. There's one more important thing, which is lock. And I told you that there are certain shared structures which require that no two processes should be accessing or modifying this process table at the same time. So their access should be mutually exclusive, that if one is accessing, no other can access, and for that purpose we have a locking mechanism. And I think we have touched upon this thing on our lab, in our lab class at that day, that before any process can access this P table, it has to lock it. And if it is already locked, it has to wait for it to be unlocked. And after doing its work, process will unlock it. P table. P table is available in line number 2409 to 22412. We can verify it, 2409. 2409. See here. This struct P table. We'll be coming to this locking, unlocking mechanism later on when we'll study the synchronization module of operating system. Now, after doing all these things, we are now sort of ready to handle interrupt and system calls. Every interrupt is assigned a unique number known as interrupt request number. For example, interrupt from a keyboard and a network interface card will get a different IRQ number. On the same time, all the system calls, fork, exec, wait, open, close, all the system call would be represented by a single IRQ number. And then later on, we'll be differentiating which system call it is by another piece of code. So different interrupts from different devices, different type of exceptions would be having different IRQ numbers, with the exception of system calls, where all the system calls are represented by a single IRQ number. And I think that is 64. Kyun, Vijendra?
Yes, sir, that is 64.
That day you explained this thing. So all the system calls are represented or going to be identified by a single IRQ number, that is 64. Now there is an interrupt descriptor table which stores the information about what to do with every different interrupt number. If there is an interrupt, that interrupt will be recognized by this interrupt number. That interrupt number would be indexed into this interrupt descriptor table, and then it stores what to do with this particular interrupt. So I'm repeating it again. All the interrupts which can be generated in a particular system are going to be assigned unique number. All system calls together will be assigned a single unique number. There is an interrupt descriptor table which tells you that what to do with a particular interrupt, and that interrupt number can be used to index into that interrupt table. And this interrupt descriptor table is set up during booting up when you initialize operating system. It is there in line number 3317, TB, INIT, void, and interrupt descriptor table is initialized. Okay. Now, understanding of exact structure of IDT is not needed for you, because there is a small catch in simple OS like x86. There is a small, you can say, easiness is there in x86 because it's a small operating system. In x86 operating system, IDT entries for all interrupts point to a single generic function. I mean to say, to handle all the interrupts, kernel will start executing a generic common function known as alltrap, which is given in line number 3254. In another operating system, there may be different process of doing these things. But in V6 and XV6, what is there? Interrupt descriptor table is there, but all the interrupts are going to be initially handled by kernel, by a piece of code, piece of kernel code known as alltraps. Means for each interrupt, the kernel will start executing at this common function. तो फिर से एक बार, proc structure, 3 important things: pointer to kernel stack, bottom of the kernel stack, pointer to trap frame structure, pointer to context structure. Depending upon what is happening, trap frame or context structure is used. Context structure is used when a process switch is there. Trap frame is used when only mode switch is there. These two are different. They save different register in these two situations. The P table is just nothing but array of proc structure. The access to this P table has to be mutually exclusive. That's why a lock is there. To handle the interrupt, every interrupt is going to have a unique number, and this unique number is nothing but an index to the interrupt descriptor table. And what is interrupt descriptor table? It's a structure, data structure, which tells you what to do with every interrupt. In XP6, handling of interrupt starts at a common function, all traps. Any doubts to anybody up till this point of time? Any doubts? Okay. Most important, I'm again asking, any doubt to anybody? Okay. Then I'm going to ask a question, and the 3 person who can answer this first will get 5 marks in TA straightforward. If you want me to explain it again, I can explain it again, if any doubt is there. Otherwise, I'm going to ask question. So what is going to happen? Interrupt. That interrupt is going to have a number. That number is used to identify the interrupt in IDT. IDT tells what to do with every interrupt. But in XC6, for all the interrupts, kernel starts executing a code, same code for all the interrupts, known as all traps. This is what I told. Now my question is, how this happens? A user process was executing in kernel. An interrupt occurs, and suddenly all trap starts execution. How? The question is how? Who transfers the control from user process to all trap function? That's the question. 5 minutes. First 3 will get 5 marks.
Hello, sir.
Yes.
So I think first there will be a trap switching as there is an interrupt, and
Mm-hmm.
then it will be switching from the user mode to the kernel mode, and
Mm-hmm.
then there will be a context switching where where the process will be switched and kernel will take the command and call the process all traps.
Abhinav,
Yes.
whatever you are saying, is there any agent or person sitting over there to do these things?
No, no, sir. It will be handled by the kernel itself.
It will be handled by the kernel. So kernel is going to handle inter by running a all trap function, executing all trap function.
Yes, sir. Yes, sir. There will be a mode switch first.
Mode switch. Mode switch is nothing. I told you. It's a CPU thing. CPU, there is a bit in CPU which moves from 0 to 1.
Yes, yes.
That's there. But my question is something else. Who will call this all trap? Think over it.
Okay, sir.
2 minutes more. Yes, anybody can answer this. Yeah, Divyansh Upadhyay, you can answer this.
No, sir, I think my answer was same as Abhinav's. But
You people are not getting the point that
no, I'm understanding the question, but I'm not able. I don't
the
know.
problem here is if somebody else will come, you are saying kernel will come to call all trap. Now, if kernel will come to call all trap means something else has to be executed for calling all trap. Yes or no?
Sir, trap
Yes.
handler?
So you say trap handler. Trap handler will be executed, no?
Yes, sir. Trap handler will call the process, all traps.
Trap handler will call the. So what is trap handler?
Sir, it just switches the mode. Trap handler.
Trap handler switches the mode. Who told you?
Sir, it is used for system calling, like all the processes. Trap handler.
Okay, you say trap handler, anything it must be. It is running. It has to run, no? Trap handler.
Yes, sir.
And if that trap handle started running, what will happen to the registers of the user process which is already executing?
So if the strap handler starts running, the user process will wait, and
Wait
then
where? Wait where? Your CPU register will be overwritten. We have just seen in function call, even in a function, normal function call, when you are in a user mode only, and you are making a normal function call from one function to another function, you are saving some registers, no?
yes,
And
sir,
here you are saying that entirely new process will come, trap handler or whatever you are telling, and a user process will go out. What will happen to the work user process was doing?
so I'm not sure. I'm not sure, but I think the state will be stored in the register.
Who will store? And registers are going to be overwritten by your trap handler. Rajendra,
Yes, sir.
I think we will stop here, okay?
Okay, sir. That is okay.
Because this question they need to understand.
Yes, sir. लैब में सर हिंट दिया गया था इन लोगों को.
That's what I'm
Yes, sir.
saying. Fine. So I'll be giving this question as an assignment. Fine. With that lab assignment which I'm going to upload today. Okay? I'm going to give this question as an assignment.
Sir, was there some instructions, int that was told by Vijayendra sir in the lab?
What is that in instruction?
So I'm
That
not
was
sure, sir. I'm
special
just
case.
reminded
That
of
was
the
for
lab.
software interrupt.
Huh?
Yes, in case of software interrupt, that will happen here also. If the interrupt is generated by inside the user process itself, just like in the case of system calling. And a similar thing happens for also when you
No,
are.
don't tell, Rajan. Don't tell. Let them figure it out, okay? Okay, then we'll meet on Monday. Monday we have a class.
Okay, sir. Thank you, sir.
Okay, Brijan. Thank you.
Okay, sir.
Abhigyan is there or left? Brijan, you can leave.